Hi, this is Bhukya Krishna, rule number 20951, branch Aeronautical Engineering. So today my topic is relation between strain energy release rates and generalized stress intensity factors for V-shaped notches. First introduction. In the context of elasticity theory, the asymptotic stress state next to a rendered corner shaped V-notch is singular and the degree of singularity does depend on the notch opening angle. The stress field intensity is a function of the overall geometry of the component and the remotely applied loads, which is generally quantified by the notch stress intensity factors. NSIFs are the extension to shop V notches of the conventional stress intensity factors used for cracks. In the presence of sharp means zero radius V-shaped notches, the notch stress intensity factors NSIFs quantity the intensities of the asymptotic linear elastic stress distributions. They are proportional to the limit of the more 1 and 2 stress components multiplied by the distance powered 1 Ki from the notch tip and Ki being Williams O bar eigenvalues. When the notch tip radius is different from 0, the definition is no longer valid from a theoretical point of view, and the characteristic singular sharp notch field diverges from the rounded notch solution very next to the notch. Nevertheless, NSIFs continue to be used as parameters governing fracture if the notch root radius is sufficiently small with respect to the notch depth. By using stress distributions along the notch bisector h is equal to 0, modes 1 and 2 generalized stress intensity factors for V-shaped are given by the following expressions. The expressions are K1 means mode 1 is equal to under root 2 pi limit r extends to 0 r power 1 minus lambda 1 into sigma naught of r comma 0, and K2 mode 2 is equal to root 2 pi limit r extends to 0 r power 1 minus lambda 2 into t r naught into r comma 0, where lambda 1 and lambda 2 are Williams eigenvalues. In another slightly different definition reported in the literature, the exponents 1 minus sigma I lambda I embrace also 2 pi. Equations 1 and 2 involve stress distributions present on the notched bisector, where symmetric and skew symmetric stress distributions can be separated and formulated as limit condition in order to avoid any influence of the remote stress field. There is, however, a finite size region where stresses and strains are fully controlled by NSIFs. The problem is even more complicated in the presence of mode 2 load conditions. In the presence of a notch tip radius different from 0 equilibrium conditions at the notch root force SRH to be null at the edge, while the stress distribution due to sharp notch remains singular, at least when the notch angle is less than 102 degree. A recently proposed degree etc. Recently proposed an analytical approach for describing local stress field ahead of rounded V notches. The stress components were written by separating the contribution caused by the symmetric solution mode 1 from that caused by the skew symmetric solution mode 2, with reference to the coordinate system shown in figure 1. Mode 1 stresses are, so the stresses of mode 1 are sigma 0, sigma naught, sigma r, and tau r naught is equal to sigma 1 into r power sigma 1 minus 1 into a1 into, this is the matrix as shown in the given figure, where the uh, where both the real number q and the distance are not from the origin of the coordinate system and the notch tip depend on the v notch angle according to the expressions reported. These expressions were derived by Lazarian and Tovo in 1996 and Philippi et al. 202 by using Newbo's conformal mapping in an auxiliary u, v semi-infinite plane. It may be sufficient to remember here that the relation, this is a diagram that shows us coordinate system on geometrical parameters. Distance are not defined according to Lazarian and Tovo in 1996 and Philippi et al. 202 and P. Lazarian, Philippi International Journal of Solids and Structures. Here is the graph which we can observe distance from the north tip. Fig 2. Plots of the maximum principal stress A and the mode 1 notch intensity factor along the notch bisector B. Okay. While eliminating equation 1, the limit conditions are, then we get the, so it might be insufficient to remember here that the relation between Cartesian coordinates and curvilinear coordinates is x plus iy is equal to u plus iv into q, where q is a real number arranging from 1 1.0 flathead to 2.0 crack. Then the curve defined by u is equal to 0, which describes an angle equal to 2a, allows us to determine the relationship between q and 2a. On the other hand, by using the curve u equal to u naught, approximating the free edge to the notch of the notch, and in particular the relationship or not equal to u naught into q, it is possible to obtain the link between radius of the curvature q and the distance or not. Since equation 3 represents the symmetric solutions, the SOH stress component is always null along the notch bisector. Mode 2 stresses are. Here we can see the mode 2 structures. Here is the matrix we obtained. Now along the notch bisector, stress components sigma naught and sigma naught are null. In equation 3 and 4, the constants A1 and A2 need to be evaluated on the basis of the local stress distributions. All the other parameters in equation 3 and equation 4 have closed from expressions. But here, for Brayton's sake, such expressions are omitted and only the values assumed by the parameters for some typical notch angles are reported in table 1. So here is a table of the parameters from for mode 1 and mode 2 stress components. The degrees first row shows the degrees to alpha, next q, next lambda 1 and lambda 2, next mu 1 and mu 2, next xh1, xb1 and xb2, xc1 and xc2, xd1 and xd2, and omega 1 and omega 2. So this is the table we obtained from those. This is the graph for v-shaped notches with plate 2 alpha equal to 135 degrees. So we can satisfy applied also to v notches due to the weak variability of the degree of singularity when 2 alpha is less than 90 degrees. For large v notches, a more generalized expression can be derived. This expression represents a generalized form of equation 19 and can be applied also when the root radius is comparable to notch depth. That is, sigma maximum is equal to 1 plus omega bar 1 into k rho 1 means mode 1 power v by under root 2 pi r naught 1 minus lambda 1. Generally, in this presence of a very small value of notch tip radius, k suffix rho 1 power v is substituted by k1 v. However, we typically have KP1 K rho 1 mode 1 is greater than or equal to K1V. Thus, the introduction of KV1 into equation 20 might result in the underestimation of the elastic peak stress. A number of numerical analyses have been carried out to correlate the NSFs related to sharp and rounded V notches. All analyses have considered symmetric plates with double-edged notches characterized by rho by A equal to 0.0, 0.02, 0.04, 0.08, 0.16, 0.32 and 0.64. H by A equal to 2, 5, 10 and 50. Notch angle equal to 30 degree, 45 degree, 60 degree, 90 degree, 120 degree and 135 degree. Conclusion. In the presence of sharp V notches where the notch root radius is null subjected to mode 1 loading conditions, the notch stress intensity factors KV1 are recognized as parameters suitable for controlling the static behavior of brittle materials and the fatigue crack initiation phase of structural materials. When the notch root radius is different from 0, the characteristic singular sharp notch field diverges from the rounded notch solution very next to the notch. As the notch radius q increases, the usefulness of KVI rapidly decreases. Thank you.